Welcome to the 8th lecture of module 5 of mass transfer operation. In this module, we are discussing distillation operation. Before going to this lecture, let us have brief recap on our previous lecture. On our previous lecture, we have mostly discussed few important things. One is pinch points and concept of minimum reflux ratio. The second thing we have discussed here is how to calculate minimum reflux ratio by analytical method. And the third thing which we have discussed is the minimum reflux ratio calculation for the inflection points in equilibrium curve. So, these are the three important topics which we have discussed in our last lecture, and in this lecture we will mainly focus on three important things. One is subcooled liquid reflux, and second thing different stage efficiencies, and third thing we will consider use of open steam in distillation. So, let us start with the subcooled liquid reflux, that is reflux below its bubble point, and we call it subcooled reflux. So, distinguish between the return reflux, the reflux stream flowing from the accumulator to the column, and the effective reflux flowing down the column. So, if you just think about the distillation column, vapor which is coming from the top tray named as tray 1 and it goes to the condenser. So, it condenses the vapor into the liquid form. So, if it is a total condenser, it will cool all the or condense all the vapor to liquid, and then if it is cooled further below its bubble point, so that will be called as subcooled liquid. So, if that is returned from the reflux drum to the first tray at top tray as a return reflux, which is liquid flow say L naught, and D is the product which is taken out. So, L naught by D is the liquid reflux which is given from to the top tray. Now, that is the return reflux, and the another one is the effective reflux flowing down. What is that? So, there is a concern if the reflux is subcooled. So, if the reflux which is coming after the condenser to the reflux drum and then coming to the top tray, if that is subcooled, then there is a major concern for the design. So, effective reflux will consist of the return reflux plus whatever additional liquid is condensed when the cold liquid contacts vapor on the reflux tray. So, on the reflux tray what will happen, that is the top tray, the vapor is going out and reflux is coming to that tray. So, it is subcooled. So, because of the low temperature, it will condense some of the vapor which is going out from tray 1, top tray. So, the liquid flow inside the column below the reflux tray will increase. So, it is probably best to use effective reflux in minimum reflux calculation instead of the return reflux. Vapor from the top tray may sometimes be condensed and then cooled below its bubble point, that is called subcooled. In the condenser, this is called cold reflux. On entering the top tray, the cold reflux reaches its bubble point very quickly. So, because of this reaching the bubble point very quickly, what happens? The energy required is supplied by the condensation of some of the vapor on that tray. So, on that top tray, the condensation of the vapor which is going out is supplied because of the energy for this condensation is supplied by the vapor of that tray, and as a result there is no vapor flow which is coming from the top tray, that is G1 vapor from the top tray will be less, that tray lower than that trace. So, G1 which is going out, that will be less than the G2, that is the below that tray or the subsequent trays. The liquid flow rate L in the rectifying section will be larger than the reflux L naught, that is fed to the column from the condenser. As a result, the internal reflux ratio, that is R internal, is L by D will be greater than the external reflux ratio, which is defined R external is equal to L naught by D. So, this is external reflux ratio and this is called internal reflux ratio. So, since L naught is increasing to L, so the internal reflux ratio will increase. In order to calculate the internal reflux ratio, that is R internal, we need to know the liquid flow rate L. So, we have to calculate the liquid flow rate. Now, let us consider TCR is the temperature of the cold reflux and TBR is the temperature, its bubble point of the cold reflux fluid. So, energy required for heating the reflux is Q would be equal to L naught CPR MR into the temperature gradient, that is it reaches the bubble point on the tray. So, cold reflux temperature, bubble point temperature minus the cold reflux temperature, that is the temperature gradient, and so the energy required for vapor condense we can just divide by MR lambda to the left hand side. So, it will be L Q by MR lambda would be equal to L naught CPR MR TBR minus TCR divided by MR lambda. Here CPR is the specific heat of the reflux in kilojoule per kg degree centigrade and MR is its average molecular weight. This is the same as that of the vapor from the top tray, and lambda is the latent heat of condensation of the vapor, that is kilojoule per kg. So, this is basically the liquid which will increase. This is the liquid due to the condensation of the vapor, this much liquid will increase. So, then the internal liquid flow rate we can calculate L naught, L is equal to L naught plus L naught CPR into MR into TBR minus TCR divided by MR lambda. So, MR will cancelled out. So, it will be L naught plus L naught into CPR into TBR minus TCR by lambda, and again if we further simplify and divide both the sides with D. So, it will be L by D would be equal to L naught by D plus L naught by D into CPR into TBR minus TCR by lambda. So, As we know, L by D is the internal reflux ratio, L by D. So, and we can write this R internal would be R external, because R external is L naught by D. So, R internal would be equal to R external plus R external into CPR into the temperature difference divided by lambda. So, we can take R external outside. So, it would be R external into 1 plus CPR into TBR minus TCR by lambda. So, if this specific heat and the temperature, bubble point temperature and the cold reflux temperature and the lambda is known, heat capacity and specific heat, these are known, then we can calculate the internal reflux ratio. So, the equation for the rectifying operating line will then change to R y m plus 1 would be equal to R internal by R internal plus 1 into x n plus x d by R internal plus 1. Now, let us take an example to calculate the number of trays required by McCabe-Thiele method using the internal reflux ratio. A mixture of 45 mole percent of N-hexane and 55 mole percent of N-heptane is subjected to continuous fractionation in a tray column at 1 atmosphere total pressure. The distillate contains 95% N-hexane and the residue contains 5% N-hexane. The feed is saturated liquid. The vapor leaving the top of the tray tower is condensed and cooled below its bubble point. The reflux is returned to the tower at 62 degree centigrade temperature and the external reflux ratio is 2 is used. The relative volatility of N-hexane in mixture is given 2.36. Now, determine the number of ideal trays required for this separation using McCabe-Thiele method, and following data are given. So, boiling point of 95% N-hexane of reflux is 72 degree centigrade. Heat of vaporization of top product, that is 95% N-hexane, is 7500 kilocalorie per kilomole. Heat capacity of N-hexane is 25 kilocalorie per kilomole over the temperature range, and heat capacity of N-heptane is 30 kilocalorie per kilomole Kelvin, that is over the temperature range. So, heat capacity of the reflux, we can calculate CPR would be equal to 0.95, that is 95% into heat capacity of N-hexane is given, and 0.05 would be the N-heptane, that is 0.05 into 30. So, we can get CPR would be 25.25 kilocalorie per kilomole Kelvin. So, CPR we can calculate this way. Now, TBR, which is 72 degree centigrade temperature over here, and that should be TBR would be equal to 273 plus 72. So, 345 Kelvin temperature. The return reflux is at the top of the tower is 62 degree centigrade, the reflux which is coming. So, TCR it would be 273 plus 62. So, it is 335 Kelvin. So, we know that the internal reflux ratio is equal to external reflux ratio into 1 plus CPR into TBR minus TCR by lambda. Now, if we substitute the values, R internal would be equal to R external, which is given to the external reflux ratio 2 into 1 plus 25.25 into 345 minus 335 divided by lambda is given 7500. So, it would be 2.07. So, that is the internal reflux ratio. Now, the other data which are given, that is the top product is 95% N-hexane, the distillate, which is normal hexane which is 0.95, xd, and xw, the bottom products having the hexane is 0.05, and the feed is saturated liquid. So, when it is saturated liquid, so q is 1 and slope of the q line will be infinite. So, it would be a vertical line. So, from here we can calculate R internal by the operating line equation for the rectifying section is this one, y m plus 1 would be equal to R internal divided by R internal plus 1 into x n plus x d by R internal plus 1. So, if we substitute the values, it would be x d by R internal plus 1 would be equal to 0.95 by 2.07 plus 1. So, it is 0.31. So, and for the intercept of this rectifying section operating line, the intercept is 0.31, and we know the starting point xd for the stripping section operating line, and the equilibrium data which we have discussed in earlier problems. So, with the reflux with the relative volatility of 2.36, we can draw the equilibrium curve. So, equilibrium curve is blue line shown over here in this figure. Equilibrium curve we can draw, we can locate this point xd and we can locate the point that is xd by R internal plus 1, which is 0.31 over here. So, we can just draw this operating line in the rectifying section. Then we know the feed condition, that is ZF is equal to 0.45. So, which is over here, and if we go vertically it will cut over here to the 45-degree diagonal, and from that the feed condition is saturated liquid. So, q is equal to 1, and then q line, slope of the q line is infinite. So, this is the vertical line and q line is plotted over here. So, you could locate the intersection between the q line and the rectifying section operating line, and knowing the rectifying section starting point, because the bottoms contains the residue contains 5% n hexane. So, it is 0.0505 at this location on the 45-degree diagonal, and you can join these two intersection points and to get the stripping section operating line. Now, with starting from tray 1 over here from xd is equal to 1, if you draw the staircase arrangement between the operating line and the equilibrium line, you can calculate the total number of trays, ideal trays required by McCabe-Thiele method, and also you can locate the feed tray location as well. So, from this we can see that the total number of ideal plates is about 12.5. Now, we will discuss another important topic is stage efficiencies. Mass transfer limitation prevent the vapor leaving a tray from truly being in precise equilibrium with the liquid on the tray. So, although ideal trays, as we have discussed earlier, an ideal tray should reach the equilibrium between the leaving stream from that tray, basically the vapor going off from the tray and the liquid flowing down from that tray, the leaving streams they would be in equilibrium. But the mass transfer limitations prevent the vapor which is leaving on the tray being precisely in equilibrium with the liquid of that tray which is leaving down. Okay. So, consequently, the assumption of ideal trays is only an approximation. So, the ideal trays is only approximation, but actually they are not reached in equilibrium. So, an efficiency is used to represent the deviation from the equilibrium. So, efficiency has to be used which are departure or deviation from the equilibrium. There are three types of efficiencies which can be defined. One of them is overall efficiency, that is the efficiency throughout the column considered as same for all the trays. So, that is overall efficiency, and the second one is the local efficiency, and third efficiency is the mark free efficiency. So, we will just discuss one by one. And overall efficiency is the simplest choice. It is the ratio of the number of ideal trays to the number of actual trays. For a given separation, if we just assume that each stage are in equilibrium and we calculate the, or each stage we considered as ideal trays, and we calculate the number of trays required by McCabe-Thiele or whatever method, the graphical method of solution or whatever method, we can calculate the ideal trays required for a particular separation. Now, if we perform the experiments and if we see the total number of actual trays required would be much higher, or it would be higher than the ideal trays, because there is usually there is deviation from the ideal tray behavior or equilibrium tray behavior. So, if we divide the ideal trays divided by the actual number of trays required for that separation, which will give the lumped overall efficiency of each tray. A single efficiency can thus be used for the entire column, but is only accurate enough for preliminary design. So, this is basically for the preliminary design. Some improvement of this design can be achieved by using separate efficiencies for each section of the column. Like accuracy is limited because the effectiveness of mass transfer is constrained by the geometry and design of the tray, flow rates and paths of all streams, compositions and so on. So, because of several parameters which influence the effective mass transfer in a particular tray or in a particular column. So, there is deviation from tray to tray or sections to section in a distillation column. So, if we can use different efficiencies for different sections or for different tray, that would be helpful for finding out the actual tray required. The problem is really too complex to lump into a single parameter. So, when overall efficiencies are used, they should be based on performance data from similar column or laboratory test. So, if we use the overall efficiencies for a particular separation, then there should be a performance data of the similar column or laboratory test, so that we can scale up into that particular application, that what would be the actual number of trays required and what would be the efficiency, overall efficiency. The local efficiency is the most accurate option, but also it is most difficult to use. It is definitely defined at only a single point on a specific tray. So, local efficiency is the efficiency at a particular location in a particular tray. So, this point efficiency is very difficult to use, because you have so many locations in a tray and you have so many trays. So, local efficiency, although it is most accurate, but it is very difficult to use, and it only local efficiency calculate the efficiency at a single point. This is important when we have a large diameter column, we have the tray area is much bigger, where the efficiency of the tray depends on the geometry of the column or geometry of the tray. So, it is most necessary on large diameter columns where position dependency is significant. A Murphy efficiency is probably the most common choice, since it represent a workable compromise between accuracy and ease of use. So, it has the same form as a local efficiency, but is based on the tray average composition. So, it does not take the composition at a particular location to calculate the tray efficiency. In this case, the Murphy stage efficiency takes the average composition on a particular tray, but it varies from tray to tray or sections to section. So, it is very close to the local efficiency. So, it is defined by EM, Murphy stage efficiency is equal to yn minus yn plus 1 divided by y equilibrium in n stage n minus yn plus 1. So, the actual enrichment of the vapor over the nth tray, we can just write yn, this is the actual enrichment, yn minus yn plus 1 would be equal to Em into y equilibrium n minus yn plus 1. So, this is actual enrichment in that column, in that tray. So, in this case what we used to do, a pseudo equilibrium line is drawn such that its vertical distance from the operating line is Em times the distance between the operating line and the equilibrium line. So, like if you consider point O and point P over here, OS is the Em times of the total vertical distance between the operating line and the actual equilibrium line, which is blue line OP. So, staircase construction between the pseudo equilibrium line, which is pink color over here, shown over here, between this will give you the actual or real number of trays or plates required for the particular separation. So, typical values for Em is generally 0.6 to 0.75 for the shift trays, it is most common 0.6 to 0.75. We know that the liquid leaving a tray is not really the same as the tray average. So, a Murphy efficiency effectively assumes perfect mixing on that tray, because it considered the average concentration of that tray, but actually the composition which is varying throughout the tray, it is not the stream which is leaving is not exactly same as the average temperature. So, in practice we normally measure the liquid composition and get the vapor composition from an equilibrium calculation or diagram. So, in the case of multi-component system, the efficiencies are different for each component. The overall efficiency and the Murphy efficiency are not directly related, and you cannot use an average Murphy efficiency in place of an overall value. To use a local or Murphy efficiency with a graphical method, the true equilibrium line, as we said, the true equilibrium line is the blue line shown over here, is replaced with the effective equilibrium curve located between the, which is pink line, located between the operating line and the equilibrium line. The effective curve is used to count the stages. Now, in this case, note that the efficiency does not apply to the reboiler. So, the true equilibrium curve should be used for the last stage of the stripping section. So, it does not include the reboiler as an equilibrium stage in this calculation for the stage efficiency. So, to construct an effective equilibrium curve is not difficult. The effective curve is given by y effective would be equal to y plus Em into y equilibrium at that stage at n minus y Y equilibrium n is the equilibrium concentration of that tray vapor composition, and Y is the values of the operating lines or operating equations. So, Y represents the operating curve data. Now, a plot of Y effective will produce an interior line on the equilibrium diagram construction. So, the pink line drawn over here is data calculated based on Y effective. So, we will have one example to draw the effective equilibrium curve and how to calculate the number of real trays required for a particular separation. A mixture of 45 mole percent A and 55 mole percent B is subjected to continuous fractionation in a tray column at 1 atmosphere total pressure. The distillate contains 90% A and the residue contains 5% A. The feed is saturated liquid. A reflux ratio of 2.5 is used. Determine the number of real trays required for this separation. If the Murphy efficiency is 75%, the equilibrium data for the system is given over here. This is the XY data. Now, XD by R plus 1 we can calculate 0.9, XD is 0.9 divided by 2.5 plus 1. So, that is 0.257 and equilibrium data is given. So, we can calculate Y effective from the equations we have shown. So, now we can plot the data over here is known, which is 0.95. So, this should be not 90%, this is 95%, and you can calculate the intercept. So, which is over here. So, intercept, and you can plot the operating line for the rectifying section. The fit condition is given like earlier. So, you can plot the Q line for saturated liquid. So, Q line would be vertical. You know the bottom location, which is 0.05. So, you can have the stripping section operating line. Now, we have to draw the pseudo equilibrium curve with this data Y effective and the X data. You can plot the pseudo equilibrium curve shown over here with the red line. So, now the actual equilibrium data is not important to calculate the real number of trays. So, what we need to do? We need to calculate. So, to calculate Y effective we have used the stage efficiency Murphy efficiency of 0.75, and that is how we calculated the pseudo equilibrium curve. Now, if you just draw the staircase arrangement like McCabe-Thiele method between the pseudo equilibrium curve and the operating line between stripping section and the rectifying section, you will obtain the total number of real trays required for the separation, which is about 5.5. So, if you just remove the pseudo equilibrium curve and draw the staircase arrangement with the actual equilibrium curve, the number of trays required will obviously reduce, because the vertical distance between the equilibrium curve, pseudo equilibrium curve and the operating line is less than the actual equilibrium curve and the operating lines. Now, another important thing which we will discuss is the use of open steam. So, in the distillation column, in general heat to a distillation operation is supplied by reboiler. So, which is over here at the bottom, and the steam does not come in direct contact with the boiling solution. So, the solution which is coming to be separated into the different fractions, they does not come in contact with the steam over here. The boiler and mixture or solution is heated, and part of that solvent is in the vapor, which is returned as a boil off to the tower at the bottom. So, in this case the boiling solution does not come in contact with the steam. However, when separating an aqueous solution, if the residue or bottom products of water and traces of the solute, sometimes it may be convenient to feed live steam at the bottom of the tower. In this case, no, you need not to have reboiler at the bottom. So, live steam you can just inject into the tower bottom. The steam is injected as small bubbles into the liquid in the tower bottom. So, that will heat up the solution. The vapor leaving the liquid is then in equilibrium with the liquid if sufficient contact is obtained. Now, if we now use the balance equation, the overall balance on the tower and a component balance on A, this is overall balance. You had feed F and you have a steam, live steam injected is S, would be equal to your distillate and the bottoms. Now, if we do the species mole balance, F into ZF plus S into YS would be equal to dXd plus WXW. Here S is the mole per hour of steam and Ys generally no solute present in the steam. So, we considered Ys is equal to 0, the Ys is the mole fractions of A in the steam. The operating line equation for the rectifying section remains the same as derived earlier, operating line equation, but that for the stripping section is obviously different. The total mass balance and material balance of component A over a stripping envelope is, we can do that is Lm is the liquid flow out plus the steam which is given S would be equal to Gm plus 1 plus W. Then if we do the species mole balance, it would be Lm Xm plus S into 0 because there is no solute in the steam would be equal to Gm plus 1 into Ym plus 1 plus W xW. So, each terms have their usual significance as we discussed before, and we assume that the inlet steam is saturated. So, if we solve this, it would give us Ym plus 1 would be equal to Lm by Gm plus 1 into Xm minus W by Gm plus 1 into Xw. So, this is the stripping section operating line. Since there is no reboiler, Lm would be equal to W, and for saturated steam entering, so S would be equal to Gm plus 1, and then this operating line equation in the stripping section would be Ym plus 1 would be equal to W by S Xm minus W by S Xw. So, if we just take out W by S from the both terms, so it would be, we can write L by Gm plus 1 would be equal to W by S would be equal to Ym plus 1 by Xm minus Xw. So, this is L by G plus Gm plus 1 or W by S or Ym plus 1 by Xm minus Xw is the slope of the operating line in the stripping section. Now, let us take an example. An aqueous solution of ethanol which contains 60 mole percent of methanol is subjected to a fractionation at 1 atmosphere total pressure. Open steam is used as the source of heat energy at a rate of 100 kilomole per hour. The top product contains 90% methanol and the bottom products contains 5% methanol, although it is given 5%, but actually it would be 10% methanol, but considering 5%, we will know how to do the operating line equations. The feed is saturated liquid and reflux ratio of 2.5 is used. Now, we have to obtain the stripping section operating line, determine the number of ideal plates required for the given separation. The steam rate required for the separation is, we have to calculate. The equilibrium data for methanol water system at 1 atmosphere pressure is given. So, this is the equilibrium data. Now, distillate XD is 0.9 and 0.9 and feed mixture contains 60 mole percent of methanol. So, feed XF is 0.6, residue 5 mole percent of methanol. So, XW would be 0.05, 0.05. So, these data are given and reflux ratio is 2.5. So, if we plot them, so this is the starting point in the top sections of the column and this is the starting or end points in the bottom section of the columns. The feed condition is given is 0.60 mole percent. So, 0.6. So, we can locate the point on the 45° diagonal and feed is saturated liquid which is given over here. So, we can plot the Q line which is vertical from this 45° diagonal. We calculate XD by R plus 1 is 0.257. So, we can just draw the operating line in the rectifying section and we can also draw the connect the operating line in the stripping section. So, intercept of the rectifying section is 0.257, Q line vertical, ZF is equal to 0.6 saturated feed. So, and this is the equation for the stripping section operating line. So, slope of the operating line we can calculate 1.1. So, we have to calculate the obtain the stripping section operating line. So, intercept is 0.056. So, equation for the operating line for the stripping section would be y is equal to 1.11 x minus 0.056. So, this is the equation for the stripping section operating line. Now, the second part we have to do the number of ideal plates required for this separation by McCabe-Thiele method. Now, starting from this point we can calculate the number of ideal trays required. So, if we just plot the horizontal line and the vertical line. So, from starting from this point go to the equilibrium curve and go vertically to the operating line and then horizontal line and then go to vertically and then go horizontally. So, vertical line and then the horizontal line. So, if you look into this, so about four number of ideal stages are required for this particular separation. And then the third problem which is given to calculate the steam rate required for this separation. So, in order to calculate the steam rate we have to use the material balance equation. So, that is F plus S is equal to D plus W. So, feed and steam rate and then the distillate rate and the bottoms. So, steam is given 100 plus S would be equal to D plus W. Now, for saturated steam entering S would be equal to G m plus 1. So, we can write 100 plus G would be equal to D plus W, and if we just consider the species mole balance equation, it is 100 into ZF, that is 0.6 plus S into 0, that is the steam does not contain any solute, D into 0.9 plus W into 0.05. So, from here we can calculate this is 60 would be equal to D into 0.9 plus W into 0.05. So, from here W by G would be 1.11. So, G would be W by 1.11. So, we can calculate D is given 25 kilomole and W is 750 kilomole. So, we can calculate G would be equal to 750 kilomole per hour, which is 675 kilomole per hour. So, that is 12150 kg steam per hour. So, thank you for attending this lecture. So, we will continue our discussion on distillation in the next class.